Magnetic trapping. It was first proposed by David A. Preacher. Its origin is in plasma physics, but going forward, magnetic trapping has developed greatly and is now useful for many areas of physics researches. But what does it mean, and how does it work? Is it simply just by attaching an object to a magnet? Well, not quite. It actually uses magnetic field gradient to trap only neutral particles with magnetic moments. We cannot see this commonly happening around us because it happens in atomic scale, but it's actually quite interesting. So the idea is that in a magnetic field, these particles will have quantum states whose magnetic energy will either increase or decrease with increasing field depending on the orientation of the moment compared to the field. It's like releasing a ball from a certain height. Both phenomena experiences conservation of energy. Although magnetic trapping can occur if the particles have magnetic moments, there are more requirements needed for it to be stable. Imagine when you're trying to keep water inside a pot. If you cook it with a stove until the water boils, little bits of water will escape outside the pot because of high energy provided by the heat. Same happens when trapping an atom. The kinetic energy of the atom must be low enough in order not to counter the energy that comes from the magnetic field. Imagine again if there's a group consists of some people who are randomly talking to each other. If suddenly the leader steps up and talks, all of the people will focus on him. However, if we take the people to be atoms and the leader to be the external magnetic field, it applies oppositely for trapping an atom. The orientation of the magnetic moment of each atom must not move or change when an external magnetic field is applied for the trapping. Wait, after all this fuss, we still don't know how we can do magnetic trapping. Well, right now, there are lots of methods of how to do magnetic trapping, but for the sake of viewers, we'll tackle the easy ones only. The most basic one is called quadruple trap. As the name suggests, it consists of two coils because each coil can be considered a magnetic dipole, and it looks like this. These coils will carry anti-parallel alignment of current, hence by symmetry, it is easy to predict that the minimum field is located in the middle. This configuration is the simplest in terms of field formula derivation and structure or symmetry, but it has its own weakness. If atoms translate towards the origin and occupy it, there's a possibility that the magnetic moments of the atoms will be disoriented. If the moments are disoriented, then the atoms will escape, which is bad. We call this spin-flip Majorana transition. But we can add a time-dependent rotating bias field on the actual plane. This will shift the minimum from the origin and actually will rotate in a circle. And this is what actually physicists did back then. They call this the time average orbiting potential, aka top trap. Now this omega term that appears is called bias frequency, and not all omega values are eligible. The bias frequency should be higher than the oscillation frequency of the trapped particles in order to take effect. It's just like when you have 6 girls over 5 boys, then the girls will be the majority and be dominant. Another thing to mind is that there are transitions between consecutive internal quantum states which have a specific frequency. The bias frequency must be smaller than the transition frequency for the atoms to not become confused and lose their magnetic moment. It's like when the work given by your boss exceeds the maximum amount of work that you can do. It results time lag and confusion in finishing the work. Magnetic trapping has various uses and has been widely used over several areas of physics researches. The best known application is to be the last state of cooling in Bose-Einstein condensation. Researchers that utilize BEC have been developing rapidly since its establishment, such as quantum optics, quantum metrology, high-resolution spectroscopy, and quantum computing. For example, you can easily make an optical lattice from simulating the BEC, which are made of regular arrays of sites where the particles could be trapped, with all the sites interconnected by tunneling. You can easily vary the lattice spacing, the strength of the interaction between atoms, and the number density of atoms in the lattice. Another application for magnetic trapping is called an atomic chip, which are based on quantum mechanics. Such applications are already demonstrated, such as microscopic atomic clocks and memory of a quantum computer. Cool, right? Another relevant thing of magnetic trapping is that it allows precision spectroscopy to be more accurate due to limited motion of such atoms. And that's all you have to know about magnetic trapping. Hope you have a great day. Adios!